good news is we get to slow down with this topic a bit. You'll see on the front page that we're only ever doing one exercise a day, and even towards the end we get one where we're going to spend two lessons on one exercise. So we get to slow down a bit in this topic, which is great. Okay, but we do want to make sure that you really have understood the indices and surds things last year, and I'm expecting that maybe there might be a few little gaps for some people that we'll have to work on. So starting at the beginning, today we are looking at rational and irrational numbers. The top of the page, it says, real numbers are made up of many special types of numbers. These may be seen below. Rational numbers can be written as fractions. That's the key thing to remember. So here's our diagram. We have our real numbers. Believe it or not, there is such a thing as unreal numbers. You'll learn about those in extension maths if you decide to do that. It's where you square root negative numbers, okay? But for most people, we only ever worry about real numbers. And we can divide that into two basic categories, which is our rational numbers. Now, rational numbers is a lot of things. It's all your integers, which is all these ones up here on the board. Your negative numbers, negative 15, negative 7. It's 0, and it's all your positive counting numbers, whole numbers. Positives, negatives, and 0. Okay, they're your integers. Rational numbers are also your fractions. Any fraction, anything written as a fraction is a rational number. It is also all of the finite, which means terminating decimal. It doesn't even have to be a nice one. So it's 0.1538. As long as it has an end, it means that it can be written as a fraction, and that means that therefore it's going to be a rational number. And recurring decimals, we're actually going to learn a little strategy today on how you can turn recurring decimals into fractions, which makes them rational numbers as well. So it's only the things that you cannot turn into fractions or whole numbers already, only things that you can't turn into fractions that are irrational, the other side over here. So they are the non-recurring decimals, so decimals that do not have any pattern in them and they just keep going on forever. And obviously some of the special ones we know about that, although you guys would know, is this one here, pi. Okay, we know pi has so many decimal places, we haven't even found the end of it, and there is no recurring pattern to pi. Okay, so we have no way of expressing that in an exact way other than with that symbol, the pi symbol. Okay, there's another one which is e, which again you won't learn about unless you do advanced maths next year. But there is also this key one here, our surds. The surds are most of the surds that you'll see are types of irrational numbers. It says down here, a surd is an irrational number. There is a type of surd that is not an irrational number, and it's written down here, square root of 4. When I see it, square root of 4, it looks like a surd. It's got a square root sign. But because when you square root 4, you get a nice whole number, it now means it's rational, not irrational. But most of the surds that you see, like square root of 5, square root of 7, all of those other ones, they are irrational, most of them, okay? A surd can be written as a normal square root sign. They're the ones we're mostly going to be dealing with, normal square root signs. But it does also mean cubed roots, fourth roots, any other root, square root that we would want. To simplify surds, that's where the fun begins. You need to use your perfect square numbers. That's this last dot point down here. The perfect square numbers are 4, because 2 times 2 is 4, so 4 is your first squared number. 3 times 3 is 9, so 9 is the next one. It's 4 times 4, you see how you get the perfect squares? 5 times 5, 6 times 6, and you get all those perfect square numbers there. Now, usually you don't need to use numbers higher than 100. It does happen occasionally. It's mostly the ones under 100, though, that you'll be using. All right. Sorry? 2 times 2 is 4, so 4 is a perfect square, but 2 is not. So it's a number that you can square root and get a whole answer, a whole number answer. That is what a perfect square number is.
1 times 1.
Yeah, so 1 technically is as well. So yes, you could put 1 on that list, but dividing by 1 is not going to actually simplify anything, because we're not actually really making the number any smaller, are we? Okay, so that's why 1's been left off that list. All right, cool. Examples, this is what you need to do. First of all, state whether each of the following numbers is a surd or not. So the best way to tell if there's a big square root sign is to use your calculator and just type it in to see what kind of decimal you get. So square root of 5, there's a decimal. There's no obvious pattern to it. So we would say that that one is a surd. Okay? Even though there's a square root sign, yes, it looks like a surd, but remember if it comes out as a whole number, it's not anymore. All right? So that one is a surd. In other words, irrational. How about B, square root of 0.64? What do we get? Type it in, 0.64, press equals, 0.8. It's still a decimal, but it is a decimal, and you can even use your SD button there. That turns into a fraction very easily. So that means that that one is not a surd. Okay, unless it's a big yucky decimal, it is not a surd. Okay, cubed root of 27. A reminder where your cube root button is. So your normal square root button is here. You have to press shift and then that button to get the cube root button. Let's just see, oh, not there, I must have missed it. Press shift and then that button. You see the little 3 above it. And then you type in 27 equals a nice whole number, making it not a surd. And the 5th root of 25. Now we only have a square root and a cubed root button. If I want to do any further than that, I press shift and the X, this one over here, the X in the little box. And it means that it's got that little box at the top of the square root sign, and you can put any type of square root in there you want. So you put the 5 in there, saying it's a 5th root of 25 equals. So is that a surd or not a surd? Yeah. Surd, because big horrible decimal. Surd. Okay, question 2. Find the value of square root of 41 to 2 decimal places. That's literally type it in your calculator and round something to 2 decimal places. So normal square root button, type in the 41 and equals. To 2 decimal places, I need the 4 and the 0, the 3 rounds down. So 6.40 to 2 decimal places. Okay, question 3. This is the stuff that's going to be a little bit new, okay? We are going to turn some recurring decimals into fractions. Now there is a bit of a method to this, and it will seem a little bit unusual at first, but if you stick with the process, it actually becomes quite fun. Okay? I think so. I might be a little bit crazy, but anyway. They're good questions. To convert a recurring decimal into a fraction, we start by calling that decimal x. I'm going to say let x equal, and I'm going to write this decimal down as 0. Now that 4 with a line above it means that the 4 is repeating. So I'm just going to write 4, 4, 4, ... I know my 4 is repeating. Okay, what I need is I need 2 equations that both have that 4 repeating. The easiest way to do that is to multiply that equation through by 10. Okay, so I multiply both sides, not just one side. I multiply the x by 10, and I get 10x. And if I multiply that decimal by 10, that jumps the decimal point over 1 spot, and I get 4.444. All those decimals repeating again. I've just jumped it over 1 spot. Okay. What I've managed to do is I have got 2 equations there. They're right on top of each other. And both of them have the 444 repeating in them. That means I can subtract those 2 equations. Now it's written a little bit, I'm actually going to be subtracting upwards. I'm going to be going the bottom equation, subtract the top equation. So on the left side, I've got 10x, and I want to subtract 1x. Okay, so 10 take away 1, that's going to make 9x. Okay. I'm also going to do it on the right-hand side. 4.444 minus the 0.444 means all those decimals disappear, and what's left? Just the 4, which is perfect. We want to get rid of all those decimals because now we're going to be able to get a nice, lovely fraction. All I need to do is get that x by itself, divide the 9 underneath, so x is equal to 4 over 9. Yes, Hayley?
Would it always be on the 9?
Any single digit repeating is always going to be over 9, correct. However, we're going to sometimes have 2 digits repeating, 3 digits repeating. Sometimes the first digit won't be repeating, but the rest of them will. I can adjust it. So the strategy is a good one to learn. There are shortcuts. You can actually just type in 0.444444 on your calculator. If you do enough decimal places and just press equals, it will turn it into a fraction for you. But that's not the point. I want to see that you can follow a process, follow the process through, okay? Let's practice it again. Yeah.
How do you put repeated numbers on your calculator?
No, only by typing in 444 lots of times. It doesn't actually have a dot or a bar to put in there, unfortunately. Okay, this one. We have got the 4 and the 5 repeating. So the same process. We always start by saying let x equal, and I write my decimal down, 0.45. I like to have a few repetitions, 4545. I can see it repeating twice there. Okay?
You just put the dot over it.
Well, you can, but the reason I like to write it out is because I'm going to multiply it, and I want to see jumping the places over when I multiply it, okay? I want to see the decimal places when they subtract. Okay, last time I multiplied by 10, and that was because I only had to jump 1 4 to make it the same. If I have a 4 and a 5 repeating, I need to have the 4 first. I can't just jump one spot because then the 5 would be the first thing after the decimal place. Does that make sense? So what do you think I have to multiply this time? 100, good. So I'm going to have 100x, which means that I can do 2 jumps, 2 jumps over like that, which makes it 45.4545. Okay? Now I've managed to get the 4545 in the decimal place. It's all about the decimal places here. Okay? To get them the same. Okay? And they are. So now I subtract. I'm subtracting upwards. Okay? The bottom one, on the left-hand side, it's 100x minus 1x, which is 99. X's. All right, 45.4545 minus the 0.4545 is 45. And all I have to do is divide the 99 across. So 45 over 99. Now, does that simplify, that fraction?
5 over 11.
Oh, excellent. 5 over 11 simplifies down. Okay, now I know what you're thinking. 2 digits repeating means over 99, which it was, simplified down. 3 digits repeating means it would be over 999. 4 digits repeating, there's just lots of 9s. But remember I said I would throw a little spanner in the works, and here is one of them. So C, the 6 is not repeating. Okay, so it's what ruins the pattern, when there's a number in there that's not repeating. So we start the same way. We say let x equal 0.6, and it's only the 2's that are repeating, so 2, 2, 2. Remember I said I need 2 equations that have the same decimal repeating. Now that 6 is in the way. It's not repeating at all. So I have to get it out of the way first of all. If I multiply by 10, so 10x, I get 6.222. Unfortunately, those decimals are not the same, are they? This one has just 222, that one has a 6 in the way. I actually now need to do another jump because I have to have those decimals the same before I subtract. So if I just times by 10 again, okay, so 10, I'm timesing this equation by 10. So 10 times 10 means I'm at 100x. And it means I jump that decimal point over one more spot, because I'm timesing by another 10, I get 62.222. And it's those ones that both have the 2's repeating. Okay, the top one, that horrible 6 was in my way, which is why I couldn't use it. Okay, but now I have 2 that I can use. So I subtract them. starting with the bottom one. 100 take away 10 is 90. So 90x equals 62.222 minus 6.222. You don't, the 222s all disappear, but you also have to do 62 minus 6. Don't forget the minus 6 part, which makes 56. Okay, you're doing this number, subtract that number. The decimals are always going to just, those disappear easily, right? They subtract away. But I still have to do the 62 minus 6. It's not a 0. Before my other ones were all zeros there, so I didn't have another number here to subtract. But this time I do have a number that needs to be subtracted off. Okay, subtracting. Bottom one, subtract the one above it. Then all I have to do is divide by 90, both sides, to get 56 over 90. Check to see if that simplifies. And it does. Yep, sorry, what was it?
28 over 45.
Perfect. So just type that fraction into your calculator to simplify it down. Or you could do it in your head if you like to divide stuff like that. Okay, that wasn't so bad, was it?
Yes.
No. All right. Then we now get to our surds. Here they are. Hey. Surds are fun. I will brainwash you. Surds are fun. Okay. To simplify surds, you need those perfect square numbers. I'll write them down on the side of the page again. We don't technically need the 1, but you can have it if you want. 1, 4, 9, 16, 25, 36, so 6 times 6, 7 times 7, 8 times 8, 9 times 9, and I'll stop at 100. Okay, I could keep going, but we don't very often get ones bigger than that are useful. Okay, to simplify a surd, you have to be able to divide your number underneath your surd by one of those numbers over there. Okay? So, I mean, obviously 20 you could divide by 2 and 10. That doesn't help. It has to be able to divide by one of those to be able to simplify. Okay? So, 20. What number out of these can I divide 20 by? 4. Okay? So once you've found the perfect square, what you do is you split that surd. We know we need a 4, so square root of 4. That was my first number. And it's 4 times 5 that makes 20, isn't it? So it's going to be square root of 4 times square root of 5. Okay, so 4 was the perfect square, but it's 4 times 5 that makes 20. Only one of the numbers has to be a perfect square. It's only ever going to be one of the numbers that is a perfect square. Okay? Then, all you have to do is square root the perfect square number. The square root of 4 is 2, so it is 2 square root 5. And that is a simplified surd. Okay, let's try it again. We're going to do a few of these, because I know it's been a while since you've seen them.
So do you put your square thing first?
It doesn't matter if you put it second, but I like to put it first, because when you square root it, it makes it goes at the front.
Do you write the number by that?
Yeah, you write them next to each other. Okay, so let's do it again. So square root of 8 this time. We are looking at our perfect square numbers. We have to be able to use one of them. So 8 is 4 again. It's 4 times 2. So we're going to split the surd to be square root of 4 times square root of 2. Okay? Now the square root of 4, that's my perfect square. The square root of 4 is 2. So I square root that and I get the 2. And the square root of 2 just sits afterwards. It's the part that can't be simplified. So it just sits there afterwards. Okay? Let's do it again. 80. Now the bigger the number you can find, the better. 4 would work.
16.
But bigger the better. 16. Now, if you're not sure, this is what I used to do. In high school, I remember doing this. I'd get my calculator out, and I'd be like, 80. All right, let's look through those perfect square numbers, and I would sit there and check them. I'd go, let's divide by 36. No, that's not going to work. And I would just keep trying until I found the biggest number I could find that's going to work. And it is 16. So if I try 16, there it is. It's 16 times 5. Okay, so use your calculator to help you find the perfect square. So knowing that it's 80 is 16 times 5, I split that surd to be square root of 16 times square root of 5. Okay, now we've got our perfect square here. So the square root of 16 is 4. So it becomes 4 And the square root of 5 part, we can't simplify, so it just sits after it. How easy is simplifying surds, right? Yes, it is. Okay, part D, the only difference with this question is that there's a number at the front. Basically, we're still going to do the same thing. We're just going to leave that 6 sitting out the front for the first part, okay? So the 6 sits there, and I'm looking at the 18. And I'm looking at my list, which I've half covered up now. 9, perfect. 9 times 2 makes 18. So I split my surd. Square root of 9 times square root of 2. Now, the square root of 9, my perfect square, the square root of 9 is 3. I'm going to write this out the long way just so you see the steps. So it means I've got a 6, the 9 becomes a 3, and I've still got the square root of 2. Now what you'll find you'll start doing is you'll start multiplying those together straight away, and that's okay. So I just need to multiply 6 times 3, which is 18, square root of 2. Okay? Yeah, so you just multiply with that number at the end. Next page. E. Near 10. Thank you. Don't worry about the other numbers there. For the time being, focus on simplifying the surd. So let's leave the 5 and leave the 6. Okay, I'm going to leave those numbers there, and I'm focusing on that square root of 40. What perfect square number am I going to use? 8 times 5, but neither of those are perfect square numbers. I need a perfect square number. 4 times 10. So 4 is the perfect square. So square root of 4 times square root of 10. Okay, the square root of 4, that is 2. So let's change it. It's going to be 5 times 2, square root of 10 sitting at the end. Now, 5 times 2 is 10, yes. So that's 10 square root 10 over 6. And now that I'm done with the simplifying surd part, I can simplify the fraction part as well. I can simplify the whole numbers. So 10 and 6 both divide by 2. So I could do a little, let's divide by 2 and get 5 here. Divide by 2 and get a 3 there. So the final answer is 5 square root 10 over 3. Simplify completely. So simplify the surd first, and then simplify down any other fractions that are in there as well. All right, part F. If you have a square root sign over a fraction, you can actually change that. One of the surd rules is that you can change one big square root sign over a fraction to be a square root of the top number over a square root of the bottom number. Okay, so you can split, we've been splitting surds multiplying, okay, the one number into 2, but you can also do it on the divide, okay? Change it into square on the top, square on the bottom. Now doing that, the square root of 9, that 9's a perfect square. Okay, so straight away that 9, square root of 9 is 3. That one simplifies beautifully. The 75, not quite so nice, but we can simplify it. Think of your perfect square list. 25 times 3. Good. So it's square root of 25 times square root of 3.
Can you put a square root?
No, because that was a 9 before and I square rooted that. So it no longer has a square root sign anymore. The square root of 25 is the perfect square. So it becomes 5. The square root of 3 sits next to it. And we have a 3 on the bottom as well. How lovely. And we have one more question, 4. Question 4. Guys, you ready?
Yes.
Means you need to stop talking, please. Thank you. We're kind of going to go backwards in this question. What it says here, it says express these surds as a square root of a positive integer. What it's saying in its own roundabout way is I don't want to have a number at the front of my surd. It wants me to put everything underneath. I just want one surd, everything's underneath that surd. Okay? So I kind of want to reverse my simplifying process because that is a simplified surd and I want to go back to what the full surd would be. Now to go backwards, the whole number, 5, would be the same as the square root of 25, wouldn't it? Okay, so I go, oh, let's put that back into square root form. That would be the same as square root of 25. And I still have that square root of 3 sitting next to it. Once you have two surds multiplied together like that, you just multiply the numbers underneath. So 25 times 3 is 75. So they come back together and make one surd square root of 75. All right, that's it. That's all we're trying to do. We're just trying to put it back underneath the square root sign. Let's try it one more time. The 11 is what we're trying to move back under. So we change 11 to be square root of 121. Okay, so square root of 121 is 11. And we times that by the square root of 2 that is next to it. All I have to do is multiply the two numbers underneath. 121 times 2 is 242. So square root of 242. Easy. That's it. Done for the day.
If we have like this,